Let's start by analyzing the modules that we will need and the data definitions. In the module section, we will need to import the pygame library and the random library. We will use random only in the first stages of the algorithm by initializing the initial states of the tiles based on a probability of starting the game alive or dead. The first parameter we're gonna use is called res, which represents the dimensions of each of the tiles in our game. Our tiles are squares, which means that the width will be the same as the height, allowing us to use only one scalar to represent that value. The parameter dimensions is a compound data type of type tuple that contains two integers, representing the number of columns and the number of rows that our grid is gonna have. These are not pixels. They represent the total number of tiles in our grid. The next parameter is called the screen. That is the transformation of the number of columns and the number of rows into pixels to represent a screen with a width and a height. And we calculate these values in pixels by multiplying this element by the dimensions of each of the tiles. The display parameter is gonna be the surface in which we are gonna render our screen, and it is formed by calling the pygame library, display sublibrary, and the method setMode, which receives a tuple, representing the combination of width and height given in pixels. ChanceAlive is the parameter that connects with the random library, and it represents what is the probability of picking a tile that is in a state 0 or state 1 to place inside of our grid. In this case, it is a 50% chance of being either alive or dead. The frames per second represents how fast our animation is gonna run. The data definition tile is the basic unit of information in this program, and it is represented as a compound data type of type class with the same name. The constructor receives the column and the row, which is information that is valuable as positional information in order to allow us to know which neighbors this tile has around it. Those parameters are then multiplied by the resolution of each of the tiles in order to extract the particular coordinate in pixels in the width and the height of our screen. Self-state uses the random library to evaluate whether or not to start this tile with the number 1 or the number 0, being a wall or an empty space. If you're not familiar with this syntax, this is known as the ternary operator, and is basically a fancy way of writing a one-line if statement. The next attribute is next state. Remember, we don't modify the states directly during one step in the iteration. We wait until we calculated the new values for all of the different tiles, keeping everything frozen, and then in the next iteration, we update the states. Otherwise, we may have unexpected results. The next element, self.rect, is a compound data type that belongs to the class rect, which lives in the pygame library. Rect is getting instantiated by passing to its constructor 4 elements: the position in X in the screen, the position in Y in the screen, and how far we're gonna go from that point XY to the right and down, which is 3 pixels. The next element is the color, which is gonna change based on the influence of a helper function. Speaking of helper functions, we have 2. The first one is called draw. What it does is to first call another helper function called getColor. We'll talk about this one in just a minute, but what it does is basically updating the color based on the state. In line 27, we call the pygame library, draw sublibrary, and the rect method. The rect method is gonna ask for a surface to render a square, the color of that square, which has been updated in the previous line, and finally, the position and dimensions of that square, which is exactly what the self.rect component provides. The helper function getColor is simply mapping a particular state, which is an integer, into a string representing a color. In this case, if the state is 0, the color is white. Otherwise, it is black. The next element, which is the grid, is going to be a procedurally generated two-dimensional array of tiles. First, we iterate over every single number from 0 in the range of dimension 0, which is 300. So from 0 to 299, we're going to create a new tile, and we're going to put that tile inside of a row, which has been created as a listing here, an empty array. Notice that the tile receives two elements. The first one is the column, which has been updated through every single step in this for loop. The second element is frozen while this for loop is running, because it represents the number of the row. Every single tile in the same row should have the same value R, but its number C should get updated. Once we finish creating one row, we append that row to the grid, which is itself an empty array, therefore populating that array. The structure can be seen in our template for grid. This component right here is a guide that is going to tell us how to traverse a two-dimensional array. Rather than writing it every single time, we can simply copy and paste it, and is therefore one of the most important elements in the entire program. This one is optional. I recommend you to use it. However, is not essential. What this does is creating a higher order function, a function specific for this grid. It receives two arguments. The first one is a function itself. Remember, functions are known as first-class citizens, which means that they can be passed and returned as arguments to other functions. The second element is an ambiguous input for an undetermined number of arguments that this function is going to require. So we take the basis of this template for grid and we put it in here. Now, if you see this template, there is 3 dots followed by the name tile. But these 3 dots basically mean doing an action or a verb, which in programming languages, it usually means applying functions. So we can take this function that we receive and we put it here. And the first argument is the tile itself, as it is indicated inside of this template. The second element are going to be all of the arguments that this function may require to work properly. You will see in a minute the power of this higher order function. Okay, it seems that we are ready to start the coding process. We will start by following the general structure by which the pygame library writes programs. That means creating 2 functions called draw and update. These 2 functions are going to be run using an infinite loop that is going to call draw and is going to call update. The draw function is in charge of rendering pixels inside of a surface. We call this surface display, and we're going to call the method fill in order to give it a color. We're going to start with a very aposematic or easy to see color. And the reason why is because we don't want to see any of this color in the final product, in the final rendering of our image. Remember that every tile that we created in the grid is not overlapping any of their neighbors and is not leaving any gaps in between, which means that it should perfectly cover every single pixel of the screen that we are creating. To draw the tiles, we're going to call the helper function a higher order function font for grid that is going to receive a function and the arguments that are required by that function. So if we want to traverse every single tile in the grid and draw each of those tiles, what function do we need to use? Well, the tile template contains a function that receives self, which is an argument that doesn't need to be passed directly, and display, which represents the surface in which we want to draw the tile. So here, we're going to call the tile template followed by a dot, and then the name of the function called draw. Notice that I am not adding the brackets here. I do not need to call, and shouldn't, call the draw function here in this line. It's going to be the helper function font for grid that is going to be in charge of doing so. It just needs to know where to find that function before it calls it. And the next element I'm going to pass is going to be the display itself. Then I'm going to call for a handshake using the display sublibrary and the flip method In order to communicate from Python to the other programming language, that is the one that actually builds the screen and works asynchronously, that we are ready to proceed. Let's run this program and let's see what happens. Great. Our screen is rendering every single tile, and even though you can't probably see the entire screen, the dimensions seem to match the number of columns and number of rows. There is more columns than rows, so it is wider than taller. But if I try to move this window, it breaks. It says pygame window is not responding, and that means that this window is not interactive. I can't even close it. The program just halts and breaks. So I'm gonna close this program. And to fix that problem, we just need to make the window interactive. That's gonna be the first thing we do in the update function. We call a for loop that goes through every single event in the list of events of pygame. That is every single input that we make with the keyboard or clicking buttons with the mouse in the window, etc. If the event is of type quit, which is a special constant that the pygame library has, then we exit the game by calling the quit method. Notice that this is a method. Let's run the program again, and this time we are able to move the window wherever we want it to be. A nice tip. Okay, so let's apply the rules for Moore's algorithm. This time I'm gonna copy the template for grid, and I'm gonna select and fix the tabs and then uncomment the template. We need to do something to every single tile in the grid. The first thing we will do, because we need to count the neighbors, is to create local variables for the number of the row and the number of the column of this tile. Then we can call the neighbor list NS, and we can start populating it. In the game of life, we called the objects directly by the indexes relative to R and C. R and C are indexes. By calling first the grid, then specifying the number of row and the number of column that we wanted. But this time we are not sure that R-1 or R+1 exist. We are not gonna wrap this world around itself anymore. So what we need to do instead is to simply store that information in the form of a tuple, R, C. So I'm gonna copy this element and I'm gonna paste it 3 times. And then in a new line, I'm gonna paste it another 3 times, and so on. Here we have the 9 tiles that are in this neighborhood. This one is the tile of interest, which in this implementation of cellular automata doesn't go to the party. It doesn't get included in the calculations to the total number of neighbors. There is this nice looking gap. I love it. Okay, so in the previous row, we're gonna store R-1. In the row below the tile of interest, we're gonna apply R+1. The same applies for C, but vertically. So we have C-1, and here we have C+1. Remember, these are just numbers, so even if the index doesn't exist, it won't throw us any errors as least index out of range. Okay, so let's create an accumulator. Oops, something is going on with my tabs here. I'm gonna fix it. I'm gonna press Alt-Shift-F, and that fixes my tabs. Okay, so here we're gonna create an accumulator. We're gonna call it wall count, and it's gonna start at 0. Its job is to count the total number of walls that this tile has around it. So for every single neighbor in the list NS, don't lose track of the data type that these elements inside of NS represent. In previous implementations, those were compound data types of the class tile. This time that's not the case. They represent tuples, a compound data type of 2 integers. So we're gonna take R as n at index 0. And we're gonna take C as n at index 1. If R is bigger than 0 and R is less than the dimensions of the index 1, So these two conditions, these two relational expressions are going to check if this is not the first row and this is not the last row, and if the column is not the first column and the column is not the last column. If the answer to all of these questions is yes, then we are in the subdomain of tiles where every single tile has 8 neighbors. So we can proceed by counting those neighbors. So if the grid at the index R and the index C, which is the particular row and column inside of the grid, that gives us back a tile, so this is another way to call a particular tile, then we can ask if its state is equal to 1. If the answer is yes, we add 1 to the wall count. Because the states are binary, you could also simply add the state to the wall count, right? So because adding states that are 0 has no effect. Another way to write this, if you want to refactor things right away, is to simply add to the wall count the grid's state. Either way should be fine. Now, otherwise, if this is not in the subdomain of tiles that have 8 neighbors, we need to count that particular neighbor as a wall by saying wall count plus equal 1. We're almost done. After evaluating the total number of neighbors, we need to apply the rules. If the wall count is bigger than 4, then we make this tile next state equal to 1. Otherwise, if the wall count is less than 4, we make the tile's next state equal to 0. If neither of these cases is met, it means that the tile has exactly 4 neighbors with a state 1, in which case we simply use a ternary operator to make either a 1 or a 0 state if the chance of picking a value between 0 and 100 is less than 50. Otherwise, we give a 0. Now, to finish this program, we need to go through every single tile again, traversing the matrix. Let's call fun for grid. This time we're going to call a function we don't have yet that is going to be called update states, which doesn't receive any additional arguments. Here we're going to call update states, and this update states algorithm is going to receive a tile. The tile state will become the tile's next state. If we run the program once more, this time we should have Moore's algorithm. There it is. And this is a pretty simple implementation on how to create caves procedurally. It's surprisingly simple and elegant. I really like it. So I hope you get the chance to explore new applications for this particular algorithm. I use it for video game design. When you want to create games where you need to explore caves, of course, but also for 3D printing. When you generate structures like this that are in 3 dimensions, right, it have volume, you create a reticulation that can help a particular bacteria or microorganisms to live in anaerobic conditions. So you could 3D print one of these blocks and then tie it to a rock and then throw it at the ocean, right? Of course, with a cord or something. And after a couple of months, you can retrieve it and see what organisms are growing in those reticulations. The world of possibilities for these algorithms, as you can see, goes well beyond just regular implementations with computers. Okay, so let's move forward with other algorithms with cellular automata. I'll see you in the next tutorial.